fantastic place, especially I'm happy to come with my own bike. So today I like to talk about measurement-induced entanglement between quantum spin chains. And my talk is based on this paper, which we put in archive last year and recently published in ISSP, which was done in collaboration with Masahiro Hoshino and Yuto Ashida at University of Tokyo. Hoshino-san is just a second-year grad student in Ashida. Yeah, he's very smart, so yeah, you can try to invite him sometime. And actually, the title of our paper says entanglement swapping in critical quantum spin chains, which is a little bit different from the title of my talk here, because I thought, okay, so this entanglement swapping is one of the basic concepts in quantum information field. I'm not expert on quantum information, so actually I've encountered this terminology, entanglement swapping, for the first time when I tried to solve this problem. So, so first I want to explain what entanglement swapping means. So I copied this figure from some paper, but the idea is very simple. So we have 4 people, and each guy has a qubit. And in the initial state, this qubit of Alice is maximally entangled with qubit of Bob. And then qubit of Kara is maximally entangled with qubit with Danny. And maybe Alice and Danny are far away, like in spaceship or something, satellite or something. But Bob and Kara are next to each other. Then you can perform projective measurement, pair measurement between this Bob's qubit and Kara's qubit. And after doing projective measurement, this qubit of Bob is now maximally entangled with qubit of Kara. But we don't touch anything about these qubits of Alice and Danny. But the interesting point is that in the initial state, these guys are maximally entangled, and these guys are maximally entangled. And then we perform pair measurement between this Bob and Kara. And after measurement, Bob and Kara qubits are maximally entangled. Then what happens is that even though we didn't do anything about these qubits of Alice and Danny, now after the measurement, this qubit of Alice is now maximally entangled with qubit of Danny. And this is just for qubit problem, so you can easily start from maximally entangled to maximally entangled pairs and apply projection operator. Then you can find that these Alice-Danny qubits are maximally entangled. So this is called entanglement swapping, because in the initial state, entanglement was like this, and after the measurement, entanglement is in the horizontal direction. So this is a most basic setup of entanglement swapping involving 4 qubits. And what we have done in our paper, which I'm going to discuss, is kind of many-body version of this entanglement swapping. So our setup is like this. So we start from 2 spin 1/2 XXD chains. Chain 1 and chain 2. Each of the XXD chains is in the ground state. So in the initial state, there is no entanglement at all between chain 1 and chain 2. Then we split this, so you can regard this as a 2-leg with no interaction between then you split the system into two parts, left and right, let's see. And to the left, I pick one spin or one qubit from chain 1 and corresponding qubit or spin from the other chain at the same location. And then you perform bell pair measurement, projective measurement to one of the 4 maximally entangled states between these two spins. And then you do the same to the next spin. So again, you perform bell pair measurement and bell pair measurement and so on and so on. So in this left region, you perform bell pair measurement between every pair of spins. But in the right region, you don't do anything. So initially they were in the ground state, but you only perform bell pair measurement in this left region, and you don't do anything on spins on this right region. But the interesting point is that after doing this bell pair measurement, of course, this measured pair should be in one of the 4 bell pair states, maximally entangled states. Then, even though we didn't do anything about these spins, now after the measurement, these spins are now entangled in these spins belonging to different chains. So this is exactly like a many-body version of entanglement swapping. So this happens because in the initial state, each chain was in the ground state. So this unmeasured region spins were initially entangled with these guys. Likewise, these spins, denoted as A prime in this figure, were entangled with spins to the left. But by doing this measurement, you force some entanglement between these left regions. Then, because of this, this region A and region A prime must be entangled after this projective measurement. And the purpose of our study is to quantify how much entanglement occurs between this region A and A prime after this bell pair measurement. So, in other words, my talk title says measurement-induced entanglement. So initially there was no entanglement between this region A and A prime, but by doing this measurement, now entanglement is induced between these two regions. And what I want to do is to quantify the entanglement between these two regions. Okay. So, yeah, of course, we can do numerical calculation, which Hosono-san did. And I will later show some results from numerical simulations. But in order to extract some universal behavior, it's useful to introduce a field theory description. So initially we have XXZ chain, spin 1/2, the standard one. And it's very well established that the ground state and the low energy properties of this spin 1/2 XXZ chain can be described by Rattinger-Rickett, which is nothing but free boson conformal field theory in 1+1D. So the Lagrangian is just a free boson Lagrangian, and each spin operator, sigma z and sigma x, sigma y, admits some representation in terms of boson field. So for example, spin-spin correlation function can be calculated by calculating correlation functions of these operators for free boson field theory. And in my program, I have 2 XXZ chains, which was independent in the initial state. Each chain was in the ground state. So we need to introduce 2 fields, phi 1 and phi 2, to describe each chain. So the initial state before the measurement is simple like that. So each chain has corresponding boson field, phi 1 and phi 2. ground state can be regarded as a ground state or vacuum for this free boson field theory. So we have two-component free boson field theory. Yes.
The dispersion is not exactly linear, so probably there are. The dispersion is not exactly linear, so probably there are interactions.
Yeah, you're right. Yeah, yeah. Of course, if you really want to describe this precisely, yes. But so in my talks, I ignore all those irrelevant perturbations. So of course, in transport problem, it's known that even though those curvature of dispersion and so on are supposed to be irrelevant perturbation to this CFT, but for some transport problems, those are known to be very important. But not sure about this problem. Yeah, so maybe we need to eventually consider those irrelevant perturbations. But for today's talk, I forget about those irrelevant perturbations and just consider the consequence of this free boson CFT. So yeah, of course, before the measurement, this is in the ground state, completely equilibrium, so maybe does not fit the topic of this workshop. But after the measurement, of course, you have non-equilibrium state. So I hope it's okay to talk about this. Okay. Anyway, so now I want to introduce this bell pair measurement between two spins, one spin from chain 1 and the other spin from chain 2. And the bell pair states are maximally entangled states. For 2 qubits or 2 spin 1 half, there are 4, yeah, we can take 4 mutually orthogonal states, some maximally entangled basis states labeled by B1 and B2, which can take 0 and 1. So there are 4 bell pair states, 0, 0, 0, 1, 1, 0, 1, 1. And each state is defined like in this equation. So for example, if you consider 0, 0 state, so you have 0, 0, because B1 is 0. So first term is 0, 0. And the second term, minus 1 to B2. But the B2 is 0. So this factor is just 1. And then I have 1 B1 bar. And the B1 bar means you flip the qubit. You flip between 0 and 1. So when B1 is 0, 0 bar is 1. So in the end, this bell pair state 0, 0 is not 0, 0 plus 1, 1. So this 0, 1 is a qubit basis. So in terms of spin 1 half, this is nothing but up, up plus down, down. So this is nothing but SZ equals 0 state among the triplet state of 2 spin 1 halves. So suppose you did bell pair measurement, then you should get one of these 4 outcomes. Suppose you get 0, 0. And that means that after the measurement, these 2 spins must be in the state this 0, 0, very 0, 0. And because we introduced the field theory, conformal field theory, or Latin-Jarigi description of spin 1 half XXZ chain, I want to find the corresponding description of this bell pair 0, 0 state in terms of field theory. And in case of 0, 0, if you look at this formula, so both spins from chain 1 and chain 2 are pointing to the same direction in Z basis, up or down, down. But this SZ, sigma Z, admit this kind of field theory expression. And there is a uniform part and staggered part. But it depends on anisotropy. But for antiferromagnetic region, at least, this staggered part is more dominant. So to discuss a leading order effect, you can maybe forget this uniform part and focus on this staggered part. then chain 1 and chain 2 both have same SZ, sigma Z. Roughly means that this argument of cosine, this phi field must be the same between chain 1 and chain 2. So we can replace this Bell pair 0, 0 state with kind of condition phi 1 equals to phi 2 at the measured point. And likewise, but this is not, phi 1 equals to phi 2 is not quite enough to fix the kind of boundary condition. And the other condition can be obtained by considering the total SZ, because so up, up, plus, down, down is like a triplet state. SZ equals to 0 sector or total triplet. So we can consider the total Sx in terms of this boson field. And I skip the detailed analysis, but what we find is that basically this theta 1 plus theta 2, by the way, this theta is a dual field to phi. And theta 1 plus theta 2 basically gives total Sx. And because Sx must take, the total Sx takes maximal value, this theta 1 plus theta 2 must be 0. So phi 1, phi 2, there are two independent fields, but if you perform the measurement and the outcome is this Bell pair state, then this boson field must obey this particular condition at the boundary where you did this measurement. Then, so we repeat this Bell pair measurement for every pair in left region. In this figure, I'm displaying this measured region as by green. So every time you do Bell pair measurement, you get one of the outcomes, 0, 0, 0, 1, 1, 0, 1. And it's not completely random, there are some correlation, but roughly speaking, you randomly get one of the four results. But to do theoretical analysis, this genetic outcome is a bit complicated. So to simplify the problem, I want to first focus on the simplest special case. That is when all the outcome happens to be the same. Okay. Or you can say this is a forced measurement, or you do post-selection. So if you get a different result, you throw out, and you only look at the result if every measurement gives 0, 0. Of course, that's a very, very special case, but easier to analyze theoretically. So yeah, I want to discuss first a very special case when all the measurement outcomes are 0, 0. In measured region, this green region. But this purple region, I didn't do anything. Then in terms of field theory, okay, so this is a common trick which has been also used to discuss measurement-induced phase transition, conformal field theory, and so on. But we apply this measurement to ground state. But ground state in field theory can be constructed by concerning path integral in imaginary Euclidean space-time, and starting from imaginary time minus infinity, where I put some generic initial state, and do the time evolution, imaginary time evolution, for infinite amount of imaginary time. Then after the imaginary time evolution, only ground state survives. So if you consider the cut at tau equals to 0, then what you get at this time slice is nothing but the ground state wave function. And in order to discuss entanglement entropy, okay, so we already started from two component free boson field theory because we had two chains. But in order to compute entanglement entropy, we also need to prepare blanket component. And also, as I will discuss in the following, in order to compute entanglement entropy between A and A prime, which is the main quantity I want to calculate, we need to introduce a replica, so using the replica trick. So we introduce n replicas, so which means that in total, we need to consider 4n component free boson conformal field theory, because 2 from chain 1, chain 2, and 2 from blanket, and then we also need n replica, and each replica contains 4 components. So we have 4n component free boson field theory. And then, so on green region, I impose this boundary condition, phi 1 equals to phi 2, and theta 1 plus theta 2 equals to 0. But this purple region, I don't do anything. But to compute the entanglement entropy, I need to compute a trace of density matrix to reduce density matrix to the nth power. And then in unmeasured region, because we take nth power of density matrix, so in this purple region, we impose this kind of boundary condition. So for each chain, so A takes the value 1 and 2, referring to each chain. And then we also have ket component and bra component. This J is replica index, running from 1 to n. So in this purple region, because I take rho to n power, so the each field of J's replica, kept component, is smoothly connected to J plus first replica of a bra component, and so on. So the problem of computing the entanglement entropy between two unmeasured regions is reduced to the problem of calculating this kind of partition function, boundary partition function with this kind of boundary conditions. And then, so yeah, we had this problem, but for a while I didn't know how to compute this. Then I went back to this very well-known problem. So for the moment, I forget about this measurement, and also I forget about the two chains, and just consider single conformal field theory. And then, for simplicity, let's consider infinity long system, the ground state of conformal field theory. And I virtually cut finite segment of length L. Then consider the entanglement entropy between this red region and the rest of the system, blue region. And this is very well-known problem. In condensed matter literature, this is often attributed to Calabrese-Carty paper, but much earlier, this problem was studied by Jose, Larsen, and Wilczek in '94. And the result is this famous formula, central charge C over 3 times log of this length of this finite segment. And of course, I knew this, and I read this Calabrese-Carty paper many, many times. But I have to confess that somehow I didn't really understand this by heart. And often students came to ask me, oh, Professor, okay, I found this formula, but how to derive this formula? Then I was saying like, okay, you can read this Calabrese-Carty. That means that I couldn't go to the blackboard and explain by understand. But because I had to solve this two-chain problem, measurement-induced entanglement entropy, I had to understand this better. And I think I understand better. That is, I can go to the blackboard and how to derive this. So first, I want to share my understanding, which is, of course, not really new, but it's the same kind of derivation is buried in the literature, and I think even this first paper, Jose assembly check, contains equivalent discussion, but it's kind of buried in between the lines. So yeah, I've just recently figured out how to understand this. Okay. So this is this 94 paper by Jose assembly check, by the way. So I want to explain why this equation holds. But before going that, who are these authors? And of course, everyone knows Frank Wilczek. He's a Nobel laureate and recently, Time Crystal and everything, and very famous person. And honestly, I didn't quite know this Finn Larsen, but they were working in mostly high energy physics. So Larsen is now a professor at the University of Michigan or something. So he had a typical, very successful career path as a theoretical physicist. But what about this first guy, Jose? So I didn't know, so I did a Google search, and I found him, which is kind of interesting. So he's now director of some research institute, but actually not in physics. So he's now the director of Institute for Cultural Inquiry or something. He got PhD in Princeton, supervised by Frank Wilczek, during which time he wrote this entanglement entropy paper. But after getting PhD in theoretical physics, somehow he went to Columbia University to get a master's degree in German literature. And then after that, he got a PhD for his PhD thesis on paradoxical pressures in aesthetics, whatever it is. Then he went back to Germany doing the postdoc at Max Planck, but not at Max Planck, PKS, not solid state, not cosmology, but the Max Planck Institute for the History of Science in Berlin. And now he is this director of this Cultural Inquiry Institute. So yeah, he has very interesting career path. But he seems to be proud of his physics background. So he writes, his specialty is physics and German literature. Anyway, so let's discuss how to derive this family. Maybe I should do it. So first, I want to compute this Renyi entanglement entropy, and for that, I need to introduce replicas, n replicas of the same conformal field theory, and then take the partial trace. So again, using the path integral. So this is for the ground state of some conformal field theory. So we consider path integral, which corresponds to path integral on half-infinite plane, starting from imaginary time minus infinity. Then you can consider imaginary time evolution. And at this tau equals to 0 time slice, you have Then on blue region, outside your region, you first take you first take the trace. So taking trace means that within each replica, ket field is just connected to bra field. So we have boundary condition like this phi j or bra is connected to phi j or ket in blue region. But in red region, first you obtain the reduced density matrix by taking partial trace outside red region, then take its power of the reduced density matrix, then take trace, which means that each row A contains bra and ket, and by taking this nth power, ket field of J's replica is smoothly connected to bra component of J plus first replica. So this is a boundary condition you impose in this red region. Then again, this Zn is partition function of conformal field theory with this particular boundary condition. So this is very typical setup in boundary conformal field theory. That is, you have two different types of boundary condition. Then between two different boundary conditions, we can identify so-called boundary condition changing operator, which is also called twist operator. Then, so generally, this correlation function. Okay, so my partition function is related to can be interpreted as a two-point correlation function of the boundary condition changing operator for infinite, half-infinite plane. And this correlation function generally behaves as a power law of the distance, one of the distance to the power of 2 delta sigma. And this delta sigma is so-called boundary scaling dimension of this boundary condition changing operator. Then the problem is reduced to calculation of this boundary scaling dimension of boundary condition changing operator, which can be generally calculated by conformal mapping. That is, in the original setup, we had a half-infinite plane and the 2 boundary condition changing operator. But you can do the conformal mapping, sending those 2 boundary condition changing operator to imaginary time plus infinity and minus infinity. Then you have an infinity long strip, and one boundary condition on left and the other boundary condition on the right. And if you do this mapping, then the boundary scaling dimension of my boundary condition changing operator can be obtained by the ground state energy difference between this red-blue boundary condition on right and left, and you subtract the ground state energy of the reference state, that is blue-blue boundary condition on both sides. So if once you compute the ground state energy for these 2 combinations, by the way, this ground state means that I consider time evolution in vertical direction, which is generated by Hamiltonian. And then we can study the ground state for each pair of boundary conditions. And in our particular case, so this boundary condition alpha bar outside region, so bra and ket are connected within the same replica because I take a partial trace before introducing the replicas. But on this red boundary condition, so I take the nth power of reduced density matrix, means that the ket component of J's replica is connected to bra component of J plus first replica. So these are 2 boundary conditions. Then now I want to find the ground state energy for this combination of boundary conditions. So I can start from, for example, phi 1 bra, phi 1 ket, for example, and then move to the right. And then you hit this red boundary. Then phi 1 ket is smoothly connected to phi 2 bra. Then you are reflected back as phi 2 bra. Then you hit the left boundary. Then phi 2 bra is connected to phi 2 ket. Then reflected back. Then you reach the right boundary. Then phi 2 ket is now connected to phi 3 bra, and so on. So you trace field and go back and forth between 2 boundaries. And every time you are bounce back, you are switched to different component. But for this combination, starting from any choice of the component, you eventually are connected to all the component. So in the end, so this red and blue boundary condition means that this problem is reduced to just a single component conformal field theory with periodic boundary condition, because you eventually come back to the original component. But with a periodic boundary condition means you are on the link. But the circumference of this link is 2n times L, because there are 2n component for this CFT because 2 for Bura and Ket and n replicas. So 2n components are connected. So effectively, the circumference of cylinder becomes 2nl. And for conformal field theory with central charge L on a ring with periodic boundary condition of circumference 2nl, ground state energy is known to be this. So this is ground state energy for this red-blue boundary condition. But on the other hand, if you have this blue-blue boundary condition, then when you hit the boundary, Bura is connected to Ket. But then you reflect it back and reach the other boundary. So if you are Ket, then you are again connected to Bura within the same replica. So again, this problem is reduced to CFT on the ring, but the circumference is just 2L. And because each replica is independent, the ground state energy must be n times this famous formula, pi c over 6 and 1 over 2L. So the difference between these two quantities gives the boundary scaling dimension of the boundary condition changing operator, which becomes c over 12 times n minus 1 over n. Actually, you can find this expression in Calabrese-Carty or Jose-Larsen-Wilczek paper, but this can be understood as a difference between two ground state energies. And once you plug in this result, okay, maybe I don't know, but I can easily obtain the Renyi entanglement entropy for this CFT between finite segment and the rest of the system. And then for standard Von-Neumann entanglement entropy, we take the limit of n goes to 0, n goes to 1, then we can recover this famous formula c over 3 times log n. As I said, okay, so this is very well-known result. This derivation is also not really new, but now I understand better. So yeah, so it's kind of interesting that so this finite size CFT ground state formula is very often used in condensed matter physics and StatMech, first derived by Brede-Cardy, Nightingale, and Ian Affleck. And so actually this another famous formula, Jose-Larsen-Wilczek, Calabrese-Cardy, entanglement entropy formula are actually closely related. You can derive this result using this. And okay, so now I can come back to my own problem. So we have two chains and do the bell pair measurement in only one region and don't touch the rest of the system. But after doing the measurement, two unmeasured segments are now entangled with each other. And we can solve this problem by similar trick. So to recap, this unmeasured region T, because yeah, so in unmeasured region T, first we obtain the reduced density matrix for this purple part, and then take nth power of the reduced density matrix. Means that in this purple region, the Ket field of J's replica is smoothly connected to Bura component of J plus first replica. And this happens for each chain independently. But in this measured region, if all the outcomes are 0, 0, then we can impose this boundary condition. Phi of first chain is equal to phi of second chain. And this happens for each replica and each of Bura and Ket. And also at the boundary, so this phi 1 equals to phi 2 is subject to the Neumann boundary condition. This is a setup. And we want to calculate the partition function in the presence of these two differently imposed boundary conditions. And again, this problem can be interpreted as a correlation function of two boundary condition changes. Then the problem is reduced to finding the boundary scaling dimension of those boundary condition changing operator. And again, I can use the same trick. And so by conformal mapping, the program is mapped to two infinitely long strip. And in one setup, I have this T boundary condition on the left and mu boundary condition. Okay, so I should color this green, but mu boundary condition on the right. The mu boundary condition corresponds to this force measurement outcome. And as a reference, I need to subtract T boundary condition on both sides. And in our case, okay, T is same as before. So ket component of J's replica is connected to Bra component of next replica, J plus first replica. But this force measurement outcome 0, 0 corresponds to phi 1 connected to phi 2. So phi 1 is field for chain 1, is connected to field phi for chain 2 on the right boundary. So yeah, we can use a similar argument because on left, again, you can pick up one field component and move to the right, then phi 1 is connected to phi 2, then bounce back and reach the left boundary. And on the left boundary, if you are ket, then you are connected to Bra of next replica within the same chain. But if you reach the right boundary, you are connected to different chain field. So if you go back and forth, then also in this case, eventually all components are connected to all other component. That means that this left setup is equal to free boson conformal field theory on the link, but now circumference is 4n times L, because we had a 4n component and everyone is connected to everyone else. And on the right, if you impose TT, then so TT, then within each replica and within each chain, 1 and 2, it's closed within each replica and each chain. So there are 2n copies of the same free boson field theory on a link. And now the circumference of this link is just 2n. So the ground state energy in this sector is minus n times pi over 6L. And on the left, the ground state energy is minus pi over 24NL. And scaling dimension of the boundary condition changing operator is given by the difference between these two. So yeah, just following the same line of argument. Now we find the scaling dimension of the boundary condition changing operator is n over 6 minus 1 over 24n. So somewhat different combination from the more familiar, Olze-Larsen and Wilczek or Calabrese-Cardi result. But the derivation can be done in very similar way. And finally, the boundary function can be given as a power law. This power exponent is given by this scaling dimension. And so we can calculate the, I don't need log, sorry, but we can calculate the Renyi entanglement entropy, and then after deriving this Renyi entanglement entropy, we can take n goes to 1 limit, then we can derive the standard Fourier-Neumann entanglement entropy between two unmeasured regions of my problem. And the result is kind of similar to this Olze-Larsen Wilczek famous formula, but coefficient is different because scaling dimension of the boundary condition changing. Yeah.
Just to check, little l is the size of the unmeasured region, and then big L is the size of the sub-region of that region?
Yeah, big L is, sorry, the entire
I thought you were going to look at the unmeasured region and then look at a sub-region of it and look at its entanglement entropy with the residual.
Well, okay, so, sorry,
Oh, you're going to look at one of the chains, sorry. You're going to look at
yeah, so this is for,
okay. For the whole the whole
yeah.
unmeasured region on chain 1.
Yeah, so, yeah. So, yeah, so this is for system length capital L, and I do bell pair measurement for capital L minus small l, and then this is the result. Yeah, so this is similar to the standard result, but the difference is that this universal coefficient is different, 1/6 instead of 1/3. Which means that, before the measurement, originally each chain has this right and left region, and the right region has length small l, and this right region, which is not to be measured, was entangled with the rest of the system with 1/3 of this log. That was the famous Holzer-Larsen-Wilczek result. But after this bell pair measurement, so entanglement swapping occurs, but this entanglement swapping in this many-body case is not perfect, meaning that originally this unmeasured region had the 1/3 times log entanglement with the rest of the system. But after the bell pair measurement, it's kind of reduced to half. It's now 1/6 times log. And I'm not expert, but I think, and I think I checked with some experts on quantum information that there is an inequality because the original entanglement is kind of resource. So after the bell pair measurement, the new entanglement cannot be more than the original entanglement, but it can be reduced. So in the 4-qubit case I discussed in the beginning, you had the maximally entangled bell pairs, 2 bell pairs. In that case, original entanglement was log 2, log 2, log 2. And after doing the measurement, it's transformed to log 2, log 2. So in a sense, this entanglement swapping was perfect. 100% of entanglement was just transferred. But in this case, this swapping is not perfect. You somehow lose 1/2 of the original entanglement. But that is consistent, I think, with general constraint that is by doing this entanglement may decrease, but cannot increase. So this 1/6 is smaller than 1/3. So this is.
Do you think if you keep other measurement outcomes, it's better or worse?
Okay, so yeah, first, yeah, for this XXZ chain, we can also consider force measurement onto 0, 1 or 1, 1 or 1, 0, and in those cases we have the same result. But of course, in general, it's not uniform. And for non-uniform outcome, we don't have a theoretical result, but I'm going to show the numerical. So this is a result. So yeah, now this is a numerical result done by Hoshino-san, and yeah, there is some even-odd effect, but if you forget about the even-odd effect, this numerical result, so this is for forced uniform outcome case, but anyway, the entanglement entropy as a function of the system size, small l over large capital L, follows this CFT prediction very well, log L, and the coefficient he obtained from fitting the numerical data is between 0.165 and 0.170. So this is in good agreement with theoretical prediction 1/6. Actually, he did this numerical calculation first and obtained this number first, and then obtain this 1.6. So then, so maybe batteries. And okay, so yeah, we can also compare Renyi entropy for general replica number n, which also agrees reasonably well. And then, as I mentioned, so far theoretically, I have only studied very special case of uniform outcome or force measurement. But if you imagine really doing this kind of measurement, then the measurement outcome is to some extent random. And I don't know yet how to handle this with CFT, but numerically he can do simulation, and for each outcome you can calculate the entanglement entropy, then take an average over all the possible measurement outcomes. And this is what he did. And basically,
excuse me, do you weight that average with the Born probabilities, or is it a uniform average?
Yeah, this is, I think, the average with the probability of getting each outcome. Yeah. And so this is a bit more complicated numerically. So he can only study relatively small system like length 12. But anyway, within this numerical simulation, the result looks very similar to the uniform outcome case. And again, this is well fitted by 0.17 times log. And 0.17 is pretty close to 1.6. So I don't know yet. This is also exactly the same as 1.6 times log, or maybe a little bit different, but pretty close to 1.6. I don't know yet. And theoretically, this situation corresponds to insertion of many boundary condition changing operators. So this is related to evaluation of correlation function of many boundary condition changing operator. But at this point, I don't know how to calculate. But after taking average, numerically the result looks similar. Okay. So yeah, and we also, well, he also calculated, did a simulation for Ising, and we have some partial understanding, but for some outcome of bare pair state, the curve looks very different. It maybe doesn't quite look like a conformal field theory result, but for some outcome, it seems to follow this log curve at least. But we have some partial understanding, but we don't yet fully understand how to deal with this guy. So yeah, to summarize, so we consider the many body version of entanglement swapping, which I could also say measurement-induced entanglement between two spin 1/2 XHZ chain. That is doing the bare pair measurement in only one region of the chain, and don't do anything on the rest of the system. But then after the measurement, somehow the entanglement is generated between two unmeasured regions. And there is a universal logarithmic behavior of entanglement entropy, and we can derive from boundary CFT. And this is kind of easy once you understand how to relate this finite size scaling of the ground state energy in case of more standard entanglement entropy within CFT. So yeah, for this kind of problem, yeah, boundary conformal field theory works well, at least in this case. But yeah, there are some mysterious results in Ising, and I also don't know exactly what happens to programs. So there are many open problems, including, okay, so at least for this case, we can replace the measurement outcome as projected bare pair states by boundary condition, which is somehow very, how to say, very rough approach, because after the measurement, you you are really in the maximally entangled pair, which is far from what we deal with in terms of conformal field theory. It's low energy approximation and so on, but somehow this still works. But how far we can push this approach, I don't know yet. And also, as I mentioned, more realistic quantity is the averaged entanglement entropy, which we study numerically, but I don't know. I don't yet have a theoretical justification. But I believe there are many interesting problems along this direction, and I'd be happy to discuss. Thank you very much.
So I guess let me ask. So, have you thought about generalizing this to cases like a 2D topologically ordered state?
Yeah, that would be interesting question, but so far I haven't done anything concrete. But that's natural question. Yeah.
Okay, can you maybe just remind me what measurement outcomes it was that didn't work for Ising? I sort of lost track of the notation. So 0, 0 means you're projecting onto the 0, 0.
Yeah, this is 0, 0 means 0, 0 up plus down down in spin language.
0, 1 is the other Bell state.
Yeah, yeah.
I see.
And so of course Ising is very anisotropic, so it's not, from general viewpoint, it's not surprising to see the different result.
Right.
Still, I don't know how to describe this 0, 1 case with CFT.
Yeah, but I guess in the fermion language, is 0, 0 has a nice description and 0, 1 doesn't? Is that the point? Or?
Yeah, perhaps. Yeah. So yeah, 0, 0 is perhaps equivalent to introducing some ZZ coupling between two chains and sending interchain coupling to infinity.